In the previous topic, we constructed a circuit that had two resistors in it that were connected in series. And we saw that the more resistors you added in series, the larger the resistance of the circuit became and the smaller the current would be. Now we're going to look at a different way of adding a second resistor into our circuit. It's called adding in parallel. If you look at the circuit diagram now, we still have our potential difference being provided at the top by our EMF source. There's a voltage V there, and remember that long line is the positive side. And now we have a resistor here, we'll call that one R1 and R2, but they're not being added end to end. The left-hand sides are joined together and the right-hand sides are joined together. They're kind of joined side by side rather than end to end. And again, we call this being connected in parallel. Now something different happens here. The current that will flow through the circuit here will reach a point where it can go in one of two directions. It can either go along through resistor 1, we'll call that current I1, or it can go along through resistor 2, we'll call that I2. And again, using our plumbing analogy, this is like a pipe that splits into two pipes. The water can flow through the left-hand side or the right-hand side. And this has a different effect than adding two pipes end to end. We'll see in a minute how to calculate that. But before we do that, let's try a little experiment one more time. This arrangement allows us to add some components in different ways. Let's start off again by putting a source of EMF, a battery, into our circuit. Again, a broken circuit, no current. Let's maybe close off this part of the circuit using a closed switch. Now we have those two parallel branches we mentioned earlier, a place where the current can divide up and go one of two ways. Let's put our light bulb into one of those branches. Now we have current flowing. You can see the light bulb glowing. Of course, what we really have here is a series circuit with a couple of dangling wires. It's not really a parallel circuit until we add in our second light bulb parallel to the first. Now we can see that we do have current flowing through both branches of the parallel circuit. What happens if we now add a third light bulb in series with that? Well, it kind of happens as we expect from the previous topic. When we add something in series, we increase the resistance and we reduce the overall current that's flowing. But what's the effect of those light bulbs being added? Let's take one of them out again. Interestingly, we didn't see much of a change in the glow at all. Maybe adding something in parallel or taking it out from parallel adds differently than adding things in series. Let's go back to our circuit diagram and see. Looking at the diagram, there's a couple of things that are important to note about these parallel circuits. Firstly, the potential difference across both of the resistors must be the same. In fact, the ends of both resistors are connected on the positive side and the other ends are joined on the negative side. So in fact, the potential difference across each resistor is the same. That means we can write the current, for example, through resistor 1, using Ohm's law, will be the potential difference divided by resistance 1. And similarly, the current through resistor 2, which has the same potential difference across it, but now a different resistor, might be a different current. The other important thing to note, of course, is that the total current through the circuit will be the potential difference divided by some total resistance. That's what we're trying to determine. How does the total resistance depend upon the resistors that are added in parallel? Well, the current must equal, the total current through the circuit that is, must equal the current in branch 1 plus the current in branch 2. The current through resistor 1 plus the current through resistor 2. Now that's interesting to think about. Why must that be so? Again, we can go back to our water analogy. The amount of water flowing through one pipe, when it gets split into two, each of those pipes must add up to the same amount of water. We haven't made any water, we haven't lost any water, and the same is true here for electric current. The charge doesn't go away, the charge doesn't magically appear. If it was flowing through the whole circuit, then the amount that goes through resistor 1 plus the amount through resistor 2 must equal the total amount through the circuit. Now we can write this down fairly easily as V over R1, that's the current through resistor 1, plus V over R2, that's the current through resistor 2, and again we can now take out the voltage here as a common term, and we've got 1 over R1 plus 1 over R2. Now if we compare this formula up here and this formula down here, we can see its current equals V over something. In fact, we can easily identify from that 1 over the total resistance of the circuit must equal 1 over resistance 1 plus 1 over resistance 2. That's quite a different effect to what we had in the series circuit. Now, the reciprocals of the resistances add to give the reciprocal of the total resistance. And that's a feature that's very common in parallel circuits. In fact, in parallel circuits, the more resistors you add in parallel, the lower the total resistance becomes. Which seems kind of strange. Haven't you added more resistance? But again, what you've given is more possible paths for the current to go through, so it will always choose a path that lowers the resistance to its lowest possible value. Now you might think about, and possibly even discuss in the discussion forums, what kinds of circuits you're familiar with. Maybe the circuits in your house, maybe the circuit in a flashlight. Again, going back to our car analogy, maybe the circuit that drives the headlights on your car. Do you expect these to be series circuits or parallel circuits? Which one will be which and why? That's a really good discussion point.